département d'informatique. Il a eu un parcours éclectique puisqu'il a commencé par faire une thèse en biologie moléculaire sur des vrais problèmes de biologie expérimentaux, sur des problèmes de mutagénèse. Et ensuite, il a évolué vers l'informatique biocomputationnelle au CNRS. Avant de partir aux États-Unis, il a passé 6 ans à Stanford, où il s'est dirigé plus vers les maths computationnelles, avec des intérêts qui sont développés peu à peu pour la physique. Et aujourd'hui, il est professeur à UC Davis. Donc on est très heureux d'avoir parmi nous, vraiment. Et merci d'avoir accepté de faire un colloque.
So, thank you, Kiron. So it's really a great pleasure for me to be here. I would not have come back, despite Henri getting me at 7:30 in the morning in the lab, saying I shouldn't leave before 7 in the evening. Anyway, it's a colloquium, so my interest is to hopefully convince you that there might be a way to look at some problems differently from what we usually do. And I'm going to use the channel of the concept of optimal transport to show you that here is a field that is exploding in mathematics, exploding in computational mathematics. And maybe there are some connections that you could find interesting for what you do. So over my talk, again, to make sure we go through sort of an understanding of what the problem is, I'll go through sort of an introduction. What do we mean by optimal transport? Then I'll define it mathematically, tell you why it's hard to solve on a computer, see what has been done to solve it a few years ago, and why it led to an explosion of the use of optimal transport. Tell you that the story is not over. We really need to look at maybe a different way of thinking of the optimal transport problem, and that's where physics is going to come in. Finally, I look at some applications for image and shape comparison, and I'll conclude with sort of some recent work we've been doing, where hopefully the reason we had to do this work will be obvious at the time we go through those applications. So let's start easy. One thing I rediscovered after 20 years in the US when I came back last year is there's something cultural about France, and this is a map of Paris if you haven't recognized it. There's something cultural about France, which is you have local stores, and maybe the most important store for many people in any city in France is a bakery. You need to buy your bread. And here, put Paris, put 5 bakeries. And as a first order approximation, in physics we like first order approximation, all bakeries produce the same amount of bread. But the first question you would need to ask yourself is, hey, those bakeries, they make bread with flour. Where do they get their flour from? No, well, put a few flour mills around Paris. Same approximation. The flour mills produce enough flour for all the bakeries in Paris. And we make it even more constraining as a system. We say that each flour mill produces enough flour for one bakery. Now, put yourself in the shoe of the person who has to organize the transport of the flour from the flour mill to the bakery. Obviously, there is no way that you're going to ask the flour mill A to deliver its flour to the bakery 5. I mean, this is loss of resources. So how do we go about solving that problem? Well, first thing we see is what's the cost of transporting the flour from one mill to one bakery. And you build a table. These are the flour mill, these are the bakery. and you have a cost. Now, as a transporter, you're going to pick the solution with the minimal cost. And you keep going through your system, and you find that A with 1 is by far the best choice, then B with 2, D with 3, C with 4, E with 5. Now, what is interesting is you can rewrite that by just giving a 1 for when a mill is associated to a bakery, and 0 when it's not. So you have a binary representation of the best transport plan you came up with for delivering the flour to the bakeries. So this is just a summary table of what's the best way to transport the flour from the flour mill to the bakeries. The interesting thing is if you take those and now think of them as matrices, and you do the element-wise multiplication of the two, gives you the total cost of transporting the flour from the mill to the bakeries. Now, do we really need the constraint that a flour mill produce just enough flour for one bakery? Is it true that all bakeries are equal and produce the same amount of bread? Well, the answer is not. I mean, we all know there are more popular bakeries. There are flour mills that produce a little bit less of flour. We're going to work now on only one. We're going to reduce the amount of assumption. The only assumption we keep is the total amount of flour produced by the flour mill is the total amount of flour needed by the bakery. But it doesn't have to be a one-to-one correspondence now. And you still have your cost matrix, but what's happening now is you allow a flour mill to provide flour to more than one bakeries. And what happened is the transport plan that you have is no more binary. It allows for multiple values on one line. And what you observe is, well, there are a few things about that transport plan that now we need to be careful. The total amount of flour that leaves flour mill A is the amount of flour produced by A. The total amount of flour reaching bakery 1 is the amount of flours that it needs. But this is encoded in this representation. The first assumption that I made when I was saying equal and a binary representation of transport, that was exactly the problem that Monge introduced in the end of the 1800s, so for military purpose. But that's how the Monge optimal transport problem was defined. The relaxed version, where you allow for transport that may be fractional, that was introduced in the 1940s by a Russian economist, Kantorovich. And that was again for military purpose. That was how to help deliver not flour, but produce to the city of Leningrad as it was surrounded by the German. So that's the history behind those. Now, let's put a little bit of math on top. I have two sets of points. S1 is the set of flour mills. For each of those flour mills, I have a mass that's associated with that, which is the amount of flour that it produces. S2 is the set of bakeries. M2 is the amount of flour that it needs. But now you can forget the word bakeries and flour mills. Just consider that as two sets of weighted points. We have the condition that the total amount of flour produced by the mill is equal to the total amount of flour needed by the bakery. So we keep that constraint. We have a cost matrix. That's the table that I was telling you about, is what's the cost of transporting a unit mass of flour from a flour mill A to a bakery B. Optimal transport is to find that transport plan that minimizes the total cost of transporting the flour from the flour mill to the bakeries. And what I have on the left is the element-wise multiplication of the two matrices that I was talking about. But I need to add some constraints. Constraint number one, well, this is a physical problem. You do not transport negative amount of flour. It doesn't look good. Second, the total amount of flour that leaves a factory needs to be the amount of flour that that factory produces. So that's the total amount that leaves, and that should be equal to the amount that it produces. This is the total amount of flour reaching a bakery, and that should be equal to the amount of flour that is needed by that bakery. Solving that problem provides two information. Information number one, well, it gives you the optimal transport plan. Information number two, it gives you the minimal cost for transporting that flour. And now this is where optimal transport is interesting. If you add the constraint that C is metric, the transport cost that you find is a metric on the measured space S1 and S2. In the literature, it's been called the Wasserstein distance. It's been called the earth mover distance. It depends on the community that works on it. So what does it provide us with? It provides us with a distance measure between sets of points on a metric measured space. So that's what optimal transport provides us with. And now you can do it on discrete sets of points, on semi-discrete. You can compare discrete distribution with a continuous distribution, or between continuous distribution. And it's been used in all those domains. And there's something interesting. Why do we want a metric? Why is it such an important element that Wasserstein is a metric, or earth movers is a metric? That comes from the triangular inequality. What does the triangular inequality tell us that's so interesting in this case? If you go from a continuous to a discrete case, you have a discretization error, a certain amount of error, because you do not capture the actual distribution. Well, the error between the distance you measure on the discrete set and the actual distance on the continuous case is smaller or equal to, comes from the triangular inequality, to the discretization error on the first set of points and the discretization error on the second set of points. So that's a key result, gives you an estimate of how much error you have in the discretization. Because of that, the field of application of optimal transport is every year there are new applications. Last year I saw something in general relativity that it was interesting that I didn't know how they could connect it to, but it's there. Obviously, and there's interesting application in music, in linguistics, obviously in chemistry, but where really there is a big hope is for machine learning. You have a distance measure. You have a distance measure. So machine learning wants a distance measure. Now, if so many fields are interested in that, that means they have found a way to solve it. I've described the math. Now, how do you make it on a computer?
I have a question.
Yes.
What do you mean Cj to be metric? I mean,
Think about Cij as a Euclidean distance between
okay,
points.
But then I want that if C is 0, it implies that I equal j. But in this case, you have bakeries and wine mills. They are different objects. I don't understand.
This is the case where this is simply all. I'll come to that later. The bakeries and the flour mills sit in a Euclidean space. They're on that map. They sit in the same metric space. So the distance then relates to that metric in that space.
But you define distance between discrete sets, but you did not define between continuous.
No, I didn't.
But is it like trivial?
No, it's not trivial. But let me go into solving that problem. Here, it's a linear problem under constraints. Many algorithms are trying to solve that problem. Those algorithms have some issues that has limited the use of optimal transport. Issue number 1, you need to build the full transport plan. So the number of variables that you have is n squared. In machine learning, n can be 1,000,000. So that means you need to find 10 to the power 12 values. That's large. Problem number 2, the time complexity is O of n cube for many of these algorithms. What does it mean? If you have 1,000,000 points, the number of operations that you need to do is 10 to the power 18. I know our computers are fast, but 10 to the power 18 is large. Takes a lot of time to solve that. So what to do? Well, yes?
Typically you take G that is complex, so it's a complex convergence.
Yes.
Which is, I guess, it's the typical case. But in Twitter you can get also non-convex.
Yes. You do not have to have convex. However, the case that are interesting is when the C is convex.
Because then you can use linear programming.
Yes. Yeah. But here's another way people have looked at the problem. Linear problem and the constraints. How could I include those constraints in the problem I try to minimize? The first problem is a positivity. Well, you regularize your problem by adding a log. A log in optimization is a barrier that prevents the value from becoming negative. Second, so you've removed that constraint. Second, those are equalities. Well, you add Lagrangian to include them in the constraints. Now that you have a Lagrangian with now, but by introducing the Lagrangian, you add new variables. You don't just have Gij, but you have the lambda I and you have the mu j. But that Lagrangian can be shown to be concave. Now that it's concave, you look at the saddle point expression. It means you compute the derivative with respect, and you find the derivative with respect to the Gij, the lambda I and the mu j. And that gives you this set of nonlinear equations. First observation, the Gij are now function of the lambda I and mu j. That means you really only, if you find the lambda I and mu j that satisfy that, you get the Gij for free. So you reduce the number of variables from n squared to n, or O of n, sorry, to 2n. Second, if you write it in more matrix format, you notice that G is diagonal of a matrix, a kernel K diagonal of a second matrix, with these expression for these vector A and B. No need to go into the detail, but just what it defines is a very neat fixed point solution to solving those equations. You start with A0, B0. You know B, you can compute A. Now that you have A, you can compute B. And you repeat the process. This is called the Sinkhorn algorithm. And it's something that is very easily implemented. That's 6 lines of codes in Python. However, well, U with an epsilon remains a metric. Careful, I say metric, it's not true. It still satisfies the triangular inequality, but it's not 0 when you compute the distance of a set to itself, because it has the entropic term. So it doesn't satisfy all 3 criteria of a metric. But it at least satisfies the triangular inequality. The limit when epsilon goes to 0 of that quantity is the real Wasserstein distance. So you regularize and you keep bringing epsilon down. However, epsilon is here the denominator. Your exponential with that epsilon is going to have some numerical issues at some point. And the number of Sinkhorn iterations becomes very large as epsilon becomes very small. Epsilon is the temperature. It's the amount of regularization you bring in your system. Yes.
That you can treat dynamically, so you say that the time evolution is proportional to the times the thing that you want to keep with a definite sign. So it gives you like a k conditions. So why?
Because you're not sure to stay concave. The KTT conditions do not guarantee that you stay concave.
But the problem that you define is not automatically complex, so you don't know that.
It depends on the Cij that you have.
Okay. Given the cost function is convex, then you can have multiple
Yes.
solutions.
Yeah.
Multiple
Yeah.
local
Uh-huh.
Okay.
Now, numerical issues, problem of convergence, has to solve these problems. And this is when I came last year. And as a side, we didn't plan to work on that, but I was mentioning to Henri this problem. And he said, you have it wrong. That's not the way to look at this problem. You have to think differently. And he convinced me. And here's how we looked at it. Well, let's look at the full space of possible transport plan, G. Oh, these are all the possible transport plan that satisfy the criteria, the constraints we have, meaning the values inside G are positive, the sum of the rows are constrained, the sum of the column are constrained. So I show it like this but obviously it doesn't look like this because it's a high dimensional space. Now, if you have a full conformational space for your variable G, statistical physics, you can compute a partition function over that space. So that partition function is the integral over the whole domain of exponential minus beta. And now I introduce a temperature in my system. If I have a partition function, I can compute the free energy, I can compute internal energy, I have all the thermodynamical property of that system. Why is that interesting? Well, first mathematical results related to that is the free energy at any temperature beta is a metric if C is a metric. Second property, the function, the free energy as a function of beta is monotonically decreasing. So it's monotonic. So if we decrease beta, we know we're going to converge to the solution. The limit when beta goes to infinity of the free energy and of the internal energy is exactly the Wasserstein distance between the two sets of points. So the math behind that is solved. It's true. However,
the Hamiltonian is unconstrained.
yes.
U is
Yeah. Now, interesting, but not really useful as we cannot compute Z. I mean, you have the mathematics that tells you that it's really useful, but if you try to compute Z, is it true? Why we can't compute it when I write it like that? Well, it's this. So I need to translate that into something I could hopefully compute. Delta function to satisfy the criterion that the sum of the rows and the sum of the columns are constrained. It's equivalent to to what we had before. Second, G, I make it positive. I can have an upper bound to the value of G. That depends on how I scale my mass. Here I put the upper bound to 1. But you could put any value here based on how you constrain your mass. Once you have that, you know that the delta function, you use Fourier to represent them as integral, gives you, there's no need to look at this. But the interesting thing is once it's written like that, you can integrate analytically over the G, meaning you can make the G disappear. And once you have that, you get an expression for your partition function. That's an integral over unconstrained variable lambda and mu with a functional f beta, but that functional depends only on lambda and mu. Once you have it like that, you go back to the math and you find that the Hessian of that effective energy is negative semi-definite with 2n minus 1 negative eigenvalue and 1 zero eigenvalue. The eigenvector corresponding to the zero eigenvalue has this form. And if you set one of the lambda or mu to 0, you get back to strictly concave functional. If you are strictly concave, saddle point approximation, you look at where it reaches that maximum. And that gives you a definition for G and the constraints that it needs to satisfy. It looks sort of like what we had with Sinkhorn, but we'll see what the differences are. You solve that system. It gives you lambda and mu at the saddle point, the mean field value for lambda and mu. Once you have the mean field value, you compute G. You have a free energy, a mean field free energy, which is an approximation of the real one, and a internal energy, a mean field internal energy. These are zero-order approximation of the real one, but even though they're zero-order approximation, they remain metric. They remain strictly monotonic, and their limit is still the true Wasserstein distance. So we replace the full system with a functional that has the mathematical properties that we need.
Your starting point when you wrote this partition function, there was a definition of the measure. So you just put the measure, just integral over
Yes.
Yeah. Come up with another measure.
You could come up with another measure. I'm not saying, and the function might be different.
So then if you just follow the different approaches, I will get different solutions.
Will it get different solution? As the limit is still the real Wasserstein distance. That's the key.
I don't know what that means. Let's think about matrix models. So the different ensembles correspond to different measures. So then the equation is different behavior with different outputs of the measure.
As long as you show that at zero temperature is the same. Hmm. What I do want to show, but related to your question, is if you compare this approach that includes the temperature with the Sinkhorn algorithm, the equations are exactly the same. The only difference is how the function g is connected to the lambda and mu. In the case of the regularized solution, it's exponential minus x. In the case of the finite temperature, it has this more complicated form. But this one is going to lead to numerical instability, while this one is very well behaved because it's monotonic and constrained between 0 and 1. So that's where we gain. Let me show you some application. First thing we did is, because there are a lot of interest in the machine learning community, let's look at what machine learning really likes to work on, computer vision, comparing images. So I took a database of 200 images that relates to 10 Japanese female, and each female, pictures have been taken of these Japanese female when they express different emotion, laughing, being angry. And you have this set of images. Now, how do we compare them if we want to use the description that relates to optimal transport? On each image, you find a set of interesting points that I call key points. Those key points, computer vision is spending a lot of effort in doing that. These are pixels that are not in a background that's completely white. They're pixels that have some differential when you look at their neighborhood. Now, you do that on the second image, and each image now is represented by a set of points. Each point, you can characterize that point with a set of features. And the distance between two key points within an image or between two images is simply the Euclidean distance between their feature vector. So you can build a cost matrix. You put a mass of 1 over the number of points for each point, and you can compute a distance between two images based on the mean field distance that I described before. This is the matrix of comparing all 213 images with the 213 images. And what do you observe? A very strong diagonal. You do observe, it's interesting, you observe that this lady seems, based on computer vision, similar to this one and similar to this one. It's probably too small to notice, but these are the only 3 female that have their hair covering their ears. So it was able to capture that. But that's not the Wasserstein distance that's capturing that. That's the key point that was capturing that. Something that is interesting is if you do a classification experiment, you put some of the images of the 10 groups of images. You take a new image, and you try to see to which group it belongs. And you look at how successful you are in doing that. What's interesting is you get to be really successful once the temperature becomes very small. Because if you have too high a temperature, the matrix is not yet informative. What about for comparing shapes? So let me present spot. So this is our pet shape for many of the computational topology problems that we use. And I found out that spot is really a physics type. Oops. So why is not? Why it's not working? How come I've lost everything? Yeah. Spot is at first at zero order approximation is a spherical cow. we call it genus zero. It is. Now, what if I want to compare two shapes using the method I just described? Here, two versions of spot. Well, I can set sets of vertices on spot 1, set of vertices on spot 2, and associate a mass over 1, the number of vertices they are. What about the cost matrix? Well, I can think of them just like for the bakeries and the flour mill. They sit in a Euclidean space. So this is the Euclidean distance between the positions of the points. And now I can minimize this quantity. However, this has zero interest for a simple reason is if spot 1 is in Davis and spot 2 is in Paris, the distance I'll get will be in thousands of kilometers, while if I put spot 1 and spot 2 in this room, it's going to be in the order of meters. So what you really want to do is add a rigid body transformation so that you can now compare the two shapes and at the same time find the best orientation between those two. And what, yeah, I have problems with why it's not doing it. I'm sorry, it looks like it doesn't want to play movies. It's not even here. How did I manage to get it to work before? Oh, it's happening. It's happening. So here, I'm just following the optimization process where I find the best orientation for the cow so that it fits with the other. I repeated that on a series of shapes, 8 shapes, just like the 10 female Japanese I had. For each shape, fluctuation in how those shapes look like. And I computed a distance matrix between those shapes, the same way I had done before. It's not as clean as what we could do with the images. I mean, there are still some improvement that are possible. It's very interesting that here you have a nice connection between these two shapes. These are, in fact, the two cats and lions.
But this matrix depends on the selection of points. So the major images
Exactly, yes. Those points, no. Those points are include, these are represented by, these are discrete shapes, so they are represented by a triangular mesh, and I did not do anything with this triangular mesh. That was given to me. So I did not select specific points. I took the whole mesh. Now, yes?
Do you do that in 3D or in
3D.
or in, and what happens if you do 2D projection?
I didn't try.
Because then you can have points that go nowhere because you need to absorb it. So it's under the under.
Yeah, so I don't know. I've never tried 2D. But here, hopefully the movie will work. No. No, where did you see a start? Oh. Do you notice something interesting here? the head. I was trying to match the head with the full cow. I told him every point on the cow needs to have something coming from the head. So what is he going to do? It's going to increase the size of the head so that it gives a good overall fit. But that's not what we want. We would like some form of partial matching. So how could we introduce that partial matching? Remember what OT is. OT is a problem where we try to minimize that quantity under those constraints where the masses are given. And the masses are set to 1 over n in the generic case. What if I let the mass fluctuate? What if I allow and defines this as a function of g, m1 and m2? If I write it like this, it's trivial to solve. I give you the answer. Put m1 and m2 at 0. All the masses at 0. Because this is going to be, all the g's are going to be 0. And this is going to be 0. And since it's positive, it's the minimum. So there's a trivial answer to the problem. If you let the mass vary, you make them fluctuate to be exactly 0. So let's add a constraint. You still transfer a total of 1 mass. There's still a trivial solution if you write it like that. That trivial solution is you put all the mass on the head on 1 point, all the mass on the cow on 1 point, and you get these 2 points to match. You get a distance of 0. So when you have that problem, you regularize your problem. You add a quantity that's going to push the system to try to distribute the mass instead of keeping them concentrated on 1 point. Once you have it like that, you can repeat the whole process I was describing before. You get a free energy that depends on lambda mu and a quantity x that imposes that the sum remains 1. The system is just a little bit more complicated, but not much more complicated. And now it allows for partial transfer. I started with images, so let me go back to images. Here, a man, a horse, and a centaur. Compare those images with the technique I described before. Do it with fixed mass, and it's going to find ways to align those masses in a way that makes sense. Just tell it to let the mass vary, and this is what's going to happen. You're going to find that the centaur and the horse are going to match mostly in this region, while the centaur and the human are going to match mainly in that region. What about our head with our cow? Now it keeps the head, it doesn't blow it, and it makes it fit with the head of the cow. So it found a partial match. And just to show you, these are the values of the mass that you find, the converged value of the mass. On the cow, these are the points corresponding to the head. These are the other points. And on the head, this is the whole distribution of mass. Let me finish with some perspective. Where do we go from here? What are the other problems? Well, there are so many other problems that are interesting. I'll start with the first one. Can we go back to Monge problem, where the assignment is binary now? No more continuous, but discrete. Henri is really interesting on that, because this is exactly the problem that online dating sites are trying to solve. What about non-rigid shape matching? You need to be very careful about how you define the distance. this time? Do you want intrinsic distance or extrinsic distance? What's the metric space? The final, and this is the problem that we've been trying to solve for months now, and we're still blocked in many aspects, is your question was, how do you compute the distance between the bakeries and the flour mills? I told you, well, I put them on a metric space. And now that they sit on the metric space, I just compute the distance in that metric space. What if the set of points sit in two different metric spaces, for which I don't know what is the common space in which those 2 points sits? Well, this is a problem that Gromov has worked on. He introduced many different ways to think about that problem, and the approach that a lot of people are really interested in is what is called Gromov-Wasserstein, where the quantity that you minimize has, you look at pairs of points on space 1, pairs of points on space 2, and instead of computing the distance directly between the point, you compare the distance between I and I prime in space x, the distance between j and j prime in space mu, and you add the transport cost for going from I to j and from I prime to g prime. Solving that, and now it's no more linear. It could be quadratic, but it could be higher than quadratic. And finding a proper representation of that system remains something that we really need to work on. So let me finish by thanking the people that have helped me all over my journey along optimal transport. Marc, who is here at Institut Pasteur. Henri, 7:30 in the morning. Everyone, obviously, at the IPHT. I would have never come back if it hadn't been such a welcoming environment. And just the day after, I do want to thank also Sylvie for what she has been bringing you in the lab for years. And next year, if I come back, fortunately, she won't be here to welcome me. And it starts with that title. Thank you for listening to Optimal Transport.
Test on the Jaffe dataset, I mean, in terms of percentage of success, or how far are you, very far, or are you competitive or not?
No, not competitive, but interestingly, for the bad reasons. What I mean by that is, if you give me a small data set with 1,000 images, and you ask me to repeat that, I do better than the distance measure they have implemented in machine learning. If you give me a database of 100 million images, which are now common in machine learning, I don't follow. I can't compute all those distances. So I'm stuck. I do not have a method that, because it scales the approach based on the finite temperature, the best I can do is O of n square. But O of n square with millions of images is still much too high compared to machine learning. In machine learning, when they minimize something, they don't even compute the whole gradient. They just stochastically look at a few directions. So they are much better in scientific computing than I am.
So I don't remember the data set by Yann Lequin, it's on the M list or something like that, letters.
100,000 letters. It's already too much. Yes. But if you have a small set of images, that's an alternative that's valuable. So the only people that comes to me related to image are people that have images from the medieval times. They don't have so many of them. They're really noisy. They can't get anything from machine learning. But that's not a big funded community. this very small community. But it's so interesting, though. I mean, intellectually, it's probably one of the really culturally interesting problems that we look at.
So at some point at the beginning you mentioned general relativity. I don't know, can you or some other physical applications if you know about in physics?
So in physical chemistry, what they try to do is when you take a molecule, you compute at each atom a electrostatic potential, or you compute a potential, and now you align the two molecules based on these values of potential that you have. So that's one application that I have seen in physical chemistry. In physics, well, Henri should be able to say.
Matching some variants of this problem in vortex theory, things like that. As models for classical.
Because in cosmology, I know that at some point some people looked at what they call Monge-Ampère-Kantorowicz.
So Monge-Ampère, it's the dual representation of that problem as a differential equation. So you can take that system and rewrite it as for very specific cost function. When the cost function is quadratic, you can rewrite it as a differential equation. So solving the Monge-Kantorowicz problem with Ampère representation is solving a differential equation.
Is it long to explain? Because this is something I would like to know. It's not. I had a similar question. We've been using thermodynamics or StatMech to represent a few transport problems.
Mm-hmm.
Do you think it could be interesting to restate, I don't know, thermodynamic principles in terms of distances, or is it free energy the distance? And otherwise, could it be of some use to stationary states of equivalent or what, or even equivalent thermodynamics to restate it as
I think you need to, I personally think it could be very interesting, but you need to find the right system for which this whole idea of a distance that relates to free energy, this was a natural extension because that's what we were looking for at the beginning. If you have a different system for which you're able to compute your free energy, you usually don't compute that free energy for the sake of comparing it with another system. So they might be, it's just a question of defining a system that you would have in two geometries, for example, in which case you can compute the free energy in the two geometries, and that could be, then you could make the extension to looking at the distance between those two geometries for your system. The interesting thing, I didn't mention that at all, but one of the beauty of looking at those type of approach is I don't need to worry about the topology of the points because I just look at the registration of the two sets of points, and it could be that the topology of the sets of points are different. That's not a hindrance, while one of the other methods I've been developing for comparing those shapes, which is to build a diffeomorphism between the two shapes. Well, when you build a diffeomorphism, it's only going to work if the two shapes have the same genus. Because if they have different genus, you can. How do you build a diffeomorphism between a sphere and a torus?
What if you have a mirror image?
Those are the interesting case. Yeah, no. Will it? So what I'm really interested in is this is related to your question. Are there other functions here that might work better? Are there a different way of defining different functionals that might lead to better convergence. In the completely discrete case, we come up with a very equivalent system where we only have that with a plus here. So there might be a full set of functions here, and some are better than others. Here, 2 functions. This one is clearly better than this one. But the problem is, in sort of a physical point of view, I don't know how to. I don't know how to escape this representation. We can change. You can change this, but it doesn't bring you anything because it's just a parameter that is just a constant that you add. So this one is not helping. Just scales the function. But it's the shape of the function that might be quite interesting. Yes?
I mean, I don't know, but do you know if there are generalizations which you impose instead of equality of strings on the sum, just for example, a function of equality, where you say that the baby needs at least this amount of things?
So in the last 2 years, there have been at least 20 papers that have looked at the problem with inequalities only. It came from the work of Figali at ETH. So there's a lot of theoretical and computational approach looking at this inequality only.
And related to that, do you know, I mean, if I look at the distribution of the GIJs, the ones that are different than 0,
Uh-huh.
do you know the statistical properties of them? I mean, in a typical setting, like, for example, to a random reduction of the problem, because these things may be computed.
Yes,
distributions,
and these are things we really want to see as a function of temperature, how those distributions vary. I mean, I think, and yeah, no, it's. I didn't put it on the list of things to do, but it's there. It's on one of the top on the list of things to understand. If we do thermodynamics, we should do it right, and we should start looking at transition. We should look at evolution as a function of temperature.
Vague question, but for instance, we all used to like Euclidean metrics, you know, so Euclidean metrics, so they satisfy this triangle inequality. But for instance, in number theory, equally useful are like PID metrics, which have a stronger triangle inequality, so it's actually less than maximal of two, the sum of these two. Kind of I just thought about it, maybe because even for instance, even if you think about like transporting, you know, maybe you presume that if I transport 10 kilo compared to 100 kilo, 100 kilo is 10 times more expensive, but maybe not, just one ride. And so somehow that's sort of, you know, things make me think. So are there some this Wasserstein metrics which are sort of non-Archimedean?
Not that I know, because I mean the whole point is the Wasserstein metric gets its property from that matrix C. Most people work in a Euclidean space, in which case they have a metric. If I impose an ultrametric on C, which is exactly that max of the two, what will be the consequence on W? I don't know. I haven't seen anyone working on that. But it is an interesting question. If you change the metric properties here, how does it change the metric property here? It's a completely open question.
You implied that this function is unique.
No.
You have many solutions.
You have, there depends on the matrix C that you have.
No, for given,
For?
given cost.
Yeah, there are some costs for which there might be more than one solution.